Welcome to Beyond Galileo, a program involving a series of podcasts that explore subjects and ideas surrounding the current exhibition at the University of Oklahoma's Fred Jones Jr. Museum of Art, titled Galileo's World, an Artful Observation of the Cosmos. I'm Gary Gress, representing the Department of Geography and Environmental Sustainability within the College of Atmospheric and Geographic Sciences, and I am also on the Faculty Advisory Committee for the Fred Jones Jr. Museum of Art. Each of our podcasts will have artful conversations with experts in their fields from the Norman OU campus to find out how their disciplines, including art, science, philosophy, and of course many more, bridge Galileo's world to our own. Today, our featured guest is Dr. Nathan Kaib. Nathan, I understand that you're an assistant professor of astronomy in the OU Homer L. Dodge Department of Physics and Astronomy. Your research focuses on the formation and evolution of planetary systems of both our sun and other stars. To study these processes, you run computer simulations of how orbiting objects interact with each other over a very, very long time scales. And I know you're going to relate through our discussion today how that interfaces, if you will, with the Galilean display. So to start off, a basic question, what are the processes that produce craters on the moon? Because Galileo was an aha moment, if you will, saying, look, there's topography here, there's differences here. So what's your take on that?
Right. The way the moon gets craters is from things hitting it, and those come from a couple different places in the solar system. The most common place that those small bodies that strike the moon come from is the asteroid belt. So that's this belt of rocky debris between Mars and Jupiter. So a little bit further out from the sun than the Earth is. And then there's a small minority, about 10% of them, come from kind of an icy analog of the asteroid belt, which is out beyond Neptune. That's called the Kuiper belt. And so it's just another belt of debris. And these objects, the biggest one that we know of is Pluto, which was downgraded from planetary status a few years ago. But they range in size from a couple miles across, if not smaller, all the way up to roughly 1,000 miles or something like that. The biggest ones are the rarest, and the small ones are more common. But both the asteroid belt and the Kuiper belt, the small objects that make them up, their orbits change constantly over time, and that's from the influence of the gravity of the giant planets, and that can kind of toss them into orbits that intersect the Earth and the Moon, and they can occasionally strike the Earth and the Moon.
I know you did a wonderful museum talk one evening, and the house was packed, if you will, as far as interest in this particular subject is concerned, and not only, that particular area of expertise of yours, but the entire Galilean, if you will, exhibit. Question, have you had time to look at the entire exhibit at all?
I don't know about the entire exhibit, but most of it.
Most of it?
Yeah.
Most of it? Was there anything else that interested you or captured your fascination, if you will?
That I didn't mention that night?
That you did not mention that night.
Oh, I didn't know about this.
Oh, yes, of course.
Well, actually, I didn't talk too much about Euclid's book in there. What is it? Elements of Geometry, is that right? Or okay.
Yeah, I do believe it. I do believe that was the title of it.
I made a note to mention it, and
yes.
I think I forgot because I just got flustered during the talk or something.
Yeah.
But I mean, that whole room is about understanding perspective and how light casts shadows and things like that. And so that was a big. And this kind of ties into a point of the talk, that Galileo's ability to understand that is what set him apart from other early people that were using telescopes to look at the moon. I mean, it's one thing to report how there's changing patterns on the moon, but it's another to interpret them as, the reason there are changing patterns is because the moon's surface is not perfect. It has mountains and craters, and that casts shadows. And I think that's a common theme throughout, not just in that era, but still today. I mean, it's one thing to just generically report some phenomena that you observe, but if you have the ability to interpret that, the fundamental reason behind that makes your work a lot more important and more relevant to science in general. And I think that's as true now as it was during Galileo's time.
Usually I save these surprising questions until the end, but I thought I'd toss that out
Sure.
to you. Going back to the room of favor, if you will, the room that had the Apollo missions,
Yes.
as far as the lithographs, as far as the imagery there. So how is that room to you important in changing our understanding of the solar system?
Oh, I think that room ties in obviously because Galileo totally changed our interpretation of the moon, but that another major shift in our interpretation of the moon was when we actually went to the moon in the late 60s, early 70s. And so one thing that we know from looking at the moon, when we see craters, we know that they struck the moon at some point, something struck the moon at some point, but we don't know when that happened. And so the great thing about Apollo, those missions to the moon, is when we went there, we actually brought rocks back with us from different spots on the moon. And when you take those rocks into a laboratory, you can actually figure out how old they are. So now all of a sudden, if you get the dates of different ages of different parts of the moon, you realize that, some parts of the moon that have tons and tons of craters are about 4 billion years old. Then other parts of the moon that have much fewer craters, still some craters, but much fewer, aren't that much younger. So the oldest craters were covered up, but the moon was resurfaced just a couple 100 million years after that. So the differences in ages between the parts that are extremely heavily cratered and the parts that are much less heavily cratered is a pretty small difference. And so what that tells us is that between about 4 billion years ago and 3.8 billion years ago, there was a huge drop-off in the number of objects striking the moon. And so that still today is an ongoing avenue of research in astronomy. How do you explain that sharp drop-off? And so that's something that I'm working on today, and we believe that there was a fundamental change in the structure of the solar system due to that. Oh, go ahead.
No, that's good to pursue. So how do we account for this drop-off?
So one thing we've learned, and there's other evidence, this is evidence that's not on the moon. It's actually in the Kuiper belt, which I mentioned before, by looking at the structure of the Kuiper belt. One thing we've learned is that even today, the orbits of the giant planets, so Jupiter, Saturn, Uranus, and Neptune, they aren't fixed over long time scales. So Saturn, Uranus, and Neptune are slowly migrating further and further from the sun. And the reason for that is that they're slowly kind of eating away the Kuiper belt. Their gravity scatters Kuiper belt objects inwards. So one rule of physics, it's called the conservation of angular momentum. When you scatter something inwards, you have to move out a little bit. And so as Saturn, Uranus, and Neptune are scattering the Kuiper belt inward, they're moving out. So when those Kuiper belt objects, when they get scattered inward, they don't hit Jupiter, but they start interacting with Jupiter. Jupiter does the opposite. It actually ejects Kuiper belt objects. So if Jupiter scatters something outward, it has to move in. So the giant planet orbits are constantly moving around. And when you model simulations of this, what you find is that it's very common for them to temporarily pass through periods where their orbits actually become very unstable and they get very eccentric, very non-circular. When that happens, the gravitational perturbations from that can destabilize all the small bodies and toss small bodies all over the solar system. And so one of these periods of instability could explain this sharp, if you're going back in time, this sharp increase in the cratering rate on the moon. And then once the instability is over, then you don't have as many craters anymore.
I'm sitting here thinking of all the questions that anybody could ask, and I'm going to say, so how many planets are accounted for now in our solar system? I know it's a loaded question. Yeah. I know it is.
I would say like 8 1/4.
We got a quarter hanging in there.
So there's suggestive evidence that there's an additional planet out there.
Yeah.
Well, first of all, we'll go back to Pluto.
Okay, let's do that.
So yeah, so Pluto is not considered a planet anymore, and that's not because Pluto changed in any way. It's very analogous to when the first asteroid was discovered back in the mid-1800s. So the first asteroid, nobody knew the asteroid belt was a thing, and as telescopes got better, we were able to see fainter objects. And Ceres, the biggest asteroid in the asteroid belt, was discovered, and everybody said, "Oh, this is a new planet. We have a new planet between Mars and Jupiter." A few years later, they found another asteroid, Vesta, second biggest asteroid in the asteroid belt. Oh, we have 2 new planets. They're kind of near each other. And then speed that up a few decades, all of a sudden we know of 30 or so asteroids. Well, you could either start keeping track of each one of those and count them as equivalent to planets, or you just change the definition of a planet, which is what happened.
Okay.
So a very similar thing happened with Pluto. So Pluto was discovered in 1930, and it was a very chance discovery. It was right on the edge of what we were capable of seeing at the time. And so there was nothing else discovered out there for a long time because we didn't have the ability to see anything that was much fainter. But finally, modern telescopes progressed to the point where Pluto would have been a fairly, not routine discovery, but much less on the bleeding edge of technology. And between 1992 and today, we've discovered something like 300 to 400 Kuiper Belt objects. These are objects very similar to Pluto that are in the Kuiper Belt. So it's very analogous to what happened in the asteroid belt.
You said we've talked that as far as your computer simulations and how you study orbiting objects interact with each other over long time scales. And how do we need to use these computer simulations to understand planetary systems and how they evolve? You've touched a little bit on that. Can you elaborate on that a little bit?
Yeah. And this kind of gets into one of the other exhibits that I was going to talk about, which was Copernicus's book concerning the revolutions of heavenly orbs. So in that book, and that's important to Galileo too, because without the idea that the Earth wasn't the center of the universe, Galileo might not have had the frame of reference to interpret all of his observations the way he did. But that book kind of portrays orbits as these very fixed paths around the sun. And so Copernicus's view wasn't exactly right, because it turns out that planets can travel in circular orbits, but most of the time they travel in elliptical orbits, so they can be slightly elongated. So Kepler is the one that pointed that out, and that was very important too. And so that's totally fine. That works completely perfectly if you have, let's say, the sun and one planet, and that's it. And it works very fine on short time scales. Like if you take a snapshot of our solar system, wait 100 years, take another snapshot, you'll see that the orbits of the planets trace out almost exact ellipses. But it does get more complicated when you add in just one more planet, because when you think about any single planet in the system, it's feeling not only the gravity of the sun, but the gravity of the other planet too. So because of that, the planet, either of those planets, is not going to travel on an exact ellipse. So if you follow the Earth, wait a year for it to do one orbit around the sun, you wait exactly a year, the Earth actually doesn't reach its exact starting position. It's slightly off, and it's off by like a matter of probably, I don't know what it is, but I would guess a few miles or something like that, which is nothing when you consider that the Earth is 93 million miles from the sun. But over long time scales, what that means is that the planets actually, if you follow the Earth over millions of years, it doesn't do an ellipse. It makes a very, very complicated path because it never retraces its path exactly. And so what we find is that planets their orbits can get very, very eccentric over like hundreds of millions of years, or in the case of the giant planets, they can actually move further away from the sun or closer to the sun. And that causes planets to, sometimes they can just kind of randomly walk into configurations that wind up being very unstable. And you could have a planet get, tossed into the sun, or completely ejected out of the solar system, or they can hit each other. And so if you take a snapshot of planetary orbits today, of any planetary system, that tells you what it's like today, but it probably had some different configuration in the past, and you have to figure out what are the possible ways that a planetary system can evolve from how we think they form to what we see today. And so that's kind of what I use computer simulations to do.
Wow. And just think, from rudimentary telescopic observations of Galileo to guys like you today. I mean, it brings me to a question I've been meaning to ask. Okay, so how did you get interested in astronomy? What led you to this?
It was
this professional path, if you will.
I don't know. I mean, it was purely random. I mean, as a kid, there was some requirement in grade school where we had to read 3 books or check 3 books out of the library.
I was hoping you would say that science project where you had the planets and.
No, sorry. Although I eventually did something like that, but and most of the time I just wouldn't read them. I wouldn't. But for some reason, I checked out a book on Mars one time and thought it was the coolest thing ever, and then ended up reading every astronomy book there was in the library and got super obsessed with it for a few years. But then I kind of forgot about it, and it wasn't until college. I was a physics major because I was still kind of interested in science, but I ended up taking a general elective astronomy course and realized that I kind of never grew out of it, and that was my favorite class in college, and I ended up pursuing it in grad school.
So you're still a kid at heart in your professional field, if you will.
Yeah, for sure.
Yeah. Well, Nate, this is great to hear from you today, and we're always so happy to have experts like you come and talk to us through these podcasts. So I do thank you. Again, today our featured guest is Dr. Nate Kaib, and or Nathan.
Nate.
Oh, okay, but we really appreciate having you today, and thanks for listening in, everybody.